Welcome, everyone. Welcome to this ninth week of Quantum Computing in a Nutshell, powered by Open Science Labs, an international organization which is out advocates for open science development as well as open source software development. As part of this lecture series, we have already discussed about the basic fundamental concepts which are associated with quantum machine learning, quantum computing, as well as quantum mechanics. On this ninth week, as I already mentioned, we are going to discuss about the cancer data analysis using quantum machine learning as well as some other algorithms which are associated with this. For this today's session, I had used PennyLen, which is an open source library, Python library, which can be able to simulate circuits, uh, which can be able to simulate quantum circuits to perform quantum based calculations. We have used some of the Wisconsin breast cancer data, which is available in open source. We had used the data, which is a very limited amount of data. We have utilized the data. We had used PyTorch, scikit-learn, as well as PennyLearn libraries to construct our circuits. We also used Legendre formulas and Bessel functions for different type of data manipulations. Also, we had compared the potential model with other traditional classical machine learning models which are available right now. This would be a comparative study in terms of quantum machine learning as well as classical machine learning. As part of our lecture series, the last week we have discussed about the Nash equilibrium based quantum machine learning financial analyzer. Before those weeks, we had used Legendre polynomial based auto encoder and decoder circuits and some other frameworks which we have already built it. For this week, we have done something in terms of medicinal analysis. First of all, let me screen share to share the informations with you. Okay. I hope my screen is visible to everyone. One second. Let me show the data here. We have around four Python modules here for our analysis, which is a native cancer quantum machine learning algorithm which uses Torch, PyTorch, PennyLearn, Scikit for other purposes as well as some other manipulation tools. Also, we had created another circuit using Legendre classification, which we have used Scikit. Also, we had created advanced quantum machine learning circuit. Also, we have created another one advanced quantum machine learning circuit using various kind of frameworks and various kind of mathematical manipulations. First of all, okay. Okay, I think there is a network interruption over there. Maybe now I'm audible. Kindly put your message in the group, the chat box. Possible. Yes, yes. Okay, 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 okay. Thank you. Uh, it is entirely muted, right? From the beginning itself, it is entirely muted. Or just now. Okay, 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 okay. Okay, I have just executed our first file, which is our native quantum machine learning file, which uses very low number of data. We have around very selective amount of data for our training model. We are using Torch PyTorch based CPU version here. The calculated data gives a cancerous analysis here. This is the plotting you have received right now. We are using Legendre and Bessel functions to test the data. We are just manipulating the data using Legendre and Bessel functions. Basically, we are converting the original data into something called as Legendre fit as well as Bessel representations. Like, let me give you an example. When you think like 55 is the data itself you have received from the particular cancerous cell membrane, like the basic core unit which is used to represent cancerous tumors are in terms of millimeter precision, maybe like 5 millimeter or 10 millimeter. What we are currently using here, it is we are representing the cancerous tumor growth in terms of millimeters, and we are converting the data into Legendre plottings, and we are evaluating the data using our particular machine learning algorithm, and we have got around, I think this terminal, we have got around 72% chance for there is cancer is there. This is the data which we have fed here, around 17 millimeter, 10 millimeter, 122 millimeter, and 1001 millimeter. And the calculated malignancy uh, probability is the cancer probability is 72 percentage. Final classification says that it could be cancerous. This is our initial model which I have developed on my own here. Now I am going to test another model which is named as pure.py, but I will explain the each and every algorithm in the end. So first of all, I would just execute the file from now on. 1 minute. Pure.py. Okay. Let me wait for a while. Now it is using a kind of different algorithm for the data analysis. Let me wait for a while for the program to be executed. Now only it is seeding the data onto it. I hope it will take some time, but I have executed this file earlier here. So I will explain it here. After collecting all the data, we have got some around uh, where it's that. I hope it is here. Yes, is the proposed chance for cancerous tumor is around 89 percentage according to this model. this particular quantum machine learning model, we have got the information as that. Okay, and another file we are going to execute this third file, the advanced quantum machine learning file, which also uses another framework to execute our data. Let me wait for a while. This circuit is created using 8 qubit circuit, which is a 8 qubit circuit. Initially, we have used around 4 qubit or 5 qubit circuits for our calculation. This is one of the most advanced circuit which we have used here, which also features the breast cancer probability as well as the diabetic risk in terms of the data which we have provided into it. Okay, I hope the thing is now visible on the screen, which shows a standard linear PCA space for the probability of cancerous cells here. The middle one, I think this is taking the entire screen right now. Okay, now you can see. This is a Legendre Bessel transformed space, which is representing the chances for the diabetes risk as well as cancerous cell growth. Also, this data, the training loss convergence across data sets, which we have used to train the data, which shows 30 futures having the data for breast cancer and 10 having the risk for diabetes. This is also the validation of ROC and AUC, which we are going to explain later on this series. We have used a dynamic 8 qubit topology. We had used controlled NOT gates for this entire execution plan here. So this is the third file which we have executed here. Let me close this file once again. Let me wait for a while for the terminal to be get closed and we can use the another final thing here. Okay. Now things are good. ADQM.py. Okay. Sorry. Python 3. ADQM.py. Okay. Let me wait for a while for the function to be get executed. From the initial file itself, we have got a 75% chance for the breast cancer analysis, and in the first one we have got around 84 percentage, and the second one we have got around 89 percentage, and the first one we have got around 79 percentage, I think so. This is the final one. Let me wait for a while for the program to be get executed, and we are going. Finally, we are going to compare the code and compare the results which we have received from all the frameworks which we have executed right now. Since my system is slightly slow, it is taking some time to process the data. Since we are doing machine learning programs, uh, traditionally it would take some time for the system to be get execute this kind of things. For your convenience, I have already taken some screenshots of this entire work. Maybe I think it is present here. I hope the screen is visible to everyone. We are using here, we are going to use, I think we should undo this. A standard linear embedding and Legender Bezier expanded version, as well as Mayer-Wallach entanglement capability, which is also a deep mathematical concept which we are going to explain later in the series, maybe like that. And also this would take a vital amount of time for explanation. I will give the entire explanation in a dedicated video, or in my particular thesis paper which I am going to release for this in the upcoming days. And this is the PQEC sample feedability and Haar random ensemble, which we are using here to represent the data in terms of the cancerous cell analogy. And we have got around 85 percentage of chance in the mean value for the breast cancer analysis, which we have done here. For those people who feels a little bit confused in terms of these all the analogies which we are used here, basically what we have done here is, once again let me draw and explain it for you, so that would be easy to understand for everybody. I hope. We have around four strategies here. We have around four strategies. One is native strategy, one is a novel strategy, one is a comparative strategy, one is a classical strategy. So we have around four different strategies for this particular breast cancer data analysis. So we have four individual executable files for this analysis. Let me explain one by one right now in the session. One second. I think I can start the code from here onwards. That would be fine to explain. What we have done here basically is we have initialized four qubits for the structure, and we had also included four raw futures for this one, and we have used a Legendre degree of 2. I mean the 2 degree of polynomials here, 2 degree of polynomial for the basic mathematical function which we are using here. Also, we have used Bessel function J0 and J1 for our analysis. We had used a QNN quantum neural network uh, states, two entangled states is 2, epoch spheres at 30, batch size is 32. We have around 32 batch size think here, and we have set it the learning rate at 0.05. The file name is saved as quantum cancer model.pth. The expanded features are used in terms of a formula 4 into 5, which gives around 20 features here in this code. We are applying Legendre Bezier transformation here in this particular part. We are doing here the Legendre expansion and the Bezier expansion. using the pre-existed modules in SciPy, and load and pre-processed data. We are loading the breast cancer data, which is available in scikit-learn, which is a open source data provided by the Wisconsin Society. And we also used the training modules here. We are using CPU based machine learning training protocols for this entire research. We have created a circuit using PennyLearn. We are using the PennyLearn to create the circuit. I hope you can see here. We have explained the weight for the analogy and so on. This is the training routine which we are using right here. I hope you can see the things. We are using a neural network for BCE loss, Adam model for the analogy, and some permutation functions and so on for the machine learning side. Also, we are using these things for our visualization purposes for the first one, for the first cancer QML file. Let me dive into the pure Python, pure analogical based circuit here. We are also using pandas, torch neural networks, pennylearn, scikit-learn for our analogy. Here we are using 4 qubits for raw features, same the bezel and things, same size of things, and we are using seeding techniques to seed the data here. And this also kind of similar to the thing, but we are using classical machine learning for this entire code, uh, which will be explained in very detail in terms of theory in my upcoming research papers, which I am going to publish in the upcoming weeks. And also we have discussed the resulted data. The thing is, the first one is entirely a different one. We have used Legendre and Bessel functions for the handling of our breast cancer data. For here, we have used a different analogy. We have used Legendre based evaluation for this entire thing. This advanced QML file, we have used Legendre and Bessel function with a higher order degree, and we have used around 8 qubit structure for this entire execution. And this another one advanced circuit, we have used a 4 qubit one, but we have set the sample data range as 1000 for our entire research. And entanglement capability, we have used Mayer-Wallach representation, which is a sample-based representation used in terms of quantum analysis. And we are used a cost contour gradient landscape, which we have seen here, which is entirely a new analogy for the quantum research. Here we are using a four-layer, the four comparative research in terms of the um, in terms of the breast cancer data analysis right here. Also, for other things, once again, this is the thing which we are using right now. Well, basically, the people who are watching this video in a recorded session may get confused what I have done here right now. Basically, I had used a Legendre and Bessel polynomial based circuit uh, based analogy for the research of the breast cancer data on the initial file. In the second file, I had used a different approach in terms of a non-linear pipeline and a quantum hybrid model. And the third file, we had used a 8 qubit, which is advanced variant of the initial model. And the fourth part, we had used a four sectional analysis and gradient analysis of the breast cancer data. The technical terms may sound confusing for the people who are watching this for the initial stage. The basic research on this particular topic is currently going on. It is going to be published next week. Also, a ton of researchers all across the world is executing this research for quite a long time. But still, we are going to travel a very long journey in the quantum machine learning in terms of cancer data analysis. The core purpose of this wonderful cancer data analysis is we can predict the cancerous cells in a very early stage using these kind of mathematical manipulations. These kind of mathematical manipulations having a ton of uh, algorithmic patterns which can be used to detect each and every non-linear algorithmic patterns. So we can easily analyze the data and find the potential risk of cancer in human body. And also we are using machine learning for finding the probability of cancerous cells in the particular data set. And for brief summary, I would like to say that I have to work way too more in this particular topic. I have to spend way more time in terms of the quantum machine learning part of the breast cancer data analysis. But the main core thing is in the upcoming years, we will have a very precise quantum machine learning model to analyze the breast cancer data as well as other clinical trial data. So that will be way too potential for understanding and diagnose these kind of deadliest diseases and clinical conditions as early as possible. So maybe this circuit and other stuff get little bit confused for you. But I hope after my research thesis is published, maybe on Zenodo or OrcXV, I will surely publish a preprint within few days. I will share the details in my Discord channel as well as my blog page. There you can find all the information regarding the methodologies which I have used here. The core concept is we are trying to build a quantum circuit which can be effectively able to predict the cancer uh, chances in the data, and we are basically comparing the quantum circuit with the classical circuit. Also we are building a hybrid quantum circuit for comparison, and also we are using a native circuit for the comparison. So we are basically using four kind of methodologies to compare a single data set, and we are comparing those values and trying to find which one is potential. And apart from the potential things, I will still try to improve my own model also, try to induce my own model into the research and try to improve it in the upcoming stages, and try to give a best clinical trial quantum machine learning model in the future. This is the problem statement which we have discussed today. These all the codes are published in my GitHub repository, which you can find as Sri Kalishwara Physics Python for Physics Calculations. Here you can find all the files which I have pushed to my GitHub repositories, and I mostly release these files under open source licenses, so there would be any barriers for you to access those codes. Also, you can try on your own. Also, For most of the programming purposes, I also use LLMs, large language models, for understanding, deeper understanding. And according to my point of view, medical quantum machine learning is the emerging field for the future. I hope that in the future we will have dedicated medicines for uh, taking away these kind of deadliest diseases like cancer, or maybe uh, dangerous viruses, or any other spread causes. In the upcoming weeks, we are going to discuss even more in depth concepts in terms of quantum machine learning, quantum computing, quantum error reduction, and other mathematical functions are associated with quantum computing. I hope this session, this recorded session, or maybe the live session, is finds useful for everybody. And I will share the other details also here, maybe in this one. For more details, you can visit my website called srikalishwarahome.blog/OSL. When you search this on Google, you will find this link. Here you can find every brochure of my quantum computing lecture series, which I will update on time. And also, here you can find some educational resources, uh, recorded session, and here you can find the join Discord button, which using this you can easily join our Discord page for further discussions, and I will update the invite link most frequently for everything. Also, you can find the lecture information in Open Science Labs official website, opensciencelabs.org. Here you can find partnerships and community partners. When you scroll down here, you will find our event details. Quantum computing in a nutshell. Every Saturday, the things are get scheduled here. Also, using this direct link, you can join the session on every Saturday at night, 10:15 p.m. Indian Standard Time, as well as other times mentioned in these brochures, like 16:45 UTC, 17:45 CET, 12:45 EDT, and 13:45 BRD, and so on. This is a global lecture series focuses in terms of quantum computing for everybody. I'm not taking these kind of lectures to the intellectual people, but for the common people who need the basic understanding in terms of quantum computing as well as quantum machine learning. This is a community based initiative. I expect one thing from all the viewers and participants. Just leave your feedback, maybe in the comment, or maybe to my email, or maybe in the direct discussions. And also, you can share these kind of sessions with other people. This would help us to do this again and again. That would be a great motivation for us. And basically, we are doing this not for money, not for financial assistance, but for the society, but for the common people who really want to know what is quantum computers. Anyway, thank you for this session. In the upcoming weeks, we are also going to dive into way more advanced topics in terms of quantum machine learning, quantum based research, and hopefully, I have find way more useful materials in terms of quantum machine learning and so on. I will also present those materials in the upcoming weeks, and we will also see more and more details about the Pennyland, Qiskit, and some other frameworks which are available in open source for quantum machine learning also. I hope this session finds you well. We will meet on the next week on 29th of August, 10:15 p.m. ISD and 16:45 UTC. Thank you, viewers. Now I am going to end this live session. No one.